And I really hope you watch these videos because they're filled with a lot of information that's helpful. Alright, so it's almost 3 in the morning here. I'm going to try to go to bed before 3:15. Let's see if I can do it before 3:14, before pi time. Let's see if I can do it. Evaluate the integral from 20 to 100 b double prime of t dt, include units. I didn't even read the problem. An inflatable bounce house is being pumped with air. Fun. The rate at which the bounce house is being uniformly pumped is differentiable. There's that word differentiable again. Come on, don't freeze on me now, computer. Is differentiable, b prime, measured in cubic feet per second. Okay, that's a rate. And those are units. So b, let's pay attention to those. This only happens on the closed interval from 0 to 120. The graph is given, and it has horizontal tangents at t equals 60, t equals 80, and t equals 100. That means that those are points of inflection. The reason I know those are points of inflection is because any extrema on b prime will automatically be points of inflection. So that might come in handy later on. Let's see, so evaluate this. So here's how we'll evaluate it. It's the integral of a derivative, a second derivative. So the antiderivative of the second derivative is the first derivative. And we'll evaluate top minus bottom. And b prime of 100 is 2. Minus b prime of 20 is 3. So we have negative 1. Now it doesn't ask you to interpret this, which is fine. If you were to interpret this, you would be saying that the net change of the rate is going to be decreasing at 1 cubic feet per second. But again, they didn't ask for interpretation. They just asked for units. And we know the units because we know it's b prime, and b prime is cubic feet per second. So our answer here is negative 1 cubic feet. I don't know why I'm doing that. Cubic feet per second. Okay, there's your answer. Number 2. That was a short one. For what values of t does the graph have a point of inflection? Haha, justify. Okay, so we already said that. That's t equals 60, 80, and 100. So that's easy. If you know what they're talking about. If you didn't know what they were talking about, you'd have to do some studying there. So t equals 60, t equals 80, and t equals 100. And 100, because b prime of t has changes direction. And I can make this a more complete sentence. B of t has a point of inflection at t equals 68 because b prime of t. Okay, good. Let's go on to the third one. Oh, I like this question. You could say changes from increasing, decrease, or decreasing, increase, or you could just say changes direction. Either one would be fine. Okay, number 3. This is a long one. At t equals 120 seconds, operator of the bounce house realizes the bounce house needs more air. Cool. The operator thinks the air which is pumped could be modeled by the differential equation dp dt. So we have a mathematician operator equals root b. Write the equation of the line tangent to the graph of b of t at t equals 130 seconds using the model value. The bounce house is 400. Whoa. Okay. That's a big one. So notice this little part that I snuck in here. 400 cubic feet at 130 seconds. If I was to write a point for that, that means that when t is 130, b, the volume of the bouncy house, is 400. So notice that b is the y value here. Let's do that first part. Write the equation of the tangent line using 130 seconds. Do not plug in 130 into root b. Instead, plug in 400 because that's what b is. So the first part is db dt evaluated at t equals 130 is equal to the square root of 400. And that's going to be 20. Okay, so that's your slope. To get the equation of the tangent line, let's go on and write that. So we'll go and do y minus 20, y minus 400 rather, because that's the b value, equals the slope 20, parentheses, t minus 130. And please keep in mind that you cannot put an x here, you have to put a t, because that's the variable. If you put an x, you will not get credit. Okay, next. Let's go ahead and plug in. So that takes care of our first part of this long problem. We got the first part done, right? The equation of the tangent line. Now, use this tangent line to estimate the value when t equals 131 seconds. So let's do that in a different color. And we're going to estimate when t equals 131. So 131 minus 130 with 20 on the outside, add the 400, and you'll get your approximation. Y of 131. And again, we're estimating when t equals 131 seconds. And you could leave your answer if you're short on time. If you wanted to do that, you would get 420 feet, cubic feet. Because we're talking about volume in a bouncy house. Okay, so that's your second answer. I'll box in our first answer here because I didn't do that. Okay, what is asked us for next? Now it says, is this estimate an over or underestimate? So I did this in the last video. If you were to have a overestimate or an underestimate for a tangent line, you would look at these four fundamental curves. A tangent line is under one and over the other when a function is either concave up or concave down. So the only way that you can tell if a tangent line is over or under is by looking at the concavity. We don't know the concavity of this function yet, so we're going to have to take a derivative of the first derivative. So we'll take the derivative here. So d2b dt squared, so taking the derivative with respect to time of both sides of the equation, the derivative of root b is going to be 1 over 2 root b. Many of you know this as bring the 1/2 down, and then it's b to the negative 1/2, which goes to 1 over 2 root b, times, and the reason I need times is because I just took the derivative of something that wasn't t with respect to t. So I needed db dt here. db dt is root b, and because dbt is root b, so I'll just write it here, root b's cancel, so I'm left with 1/2, and 1/2 is positive. And the reason I need to know 1/2 is positive is because I need my second derivative to be positive or negative, and if the second derivative is positive, I can tell where my tangent line is. So my answer, and I'll type this out here for the last part, type it on green, setting 18, is the tangent line approximation is, and again, we're concave up, so under approximation, underestimation. Tangent line approximation is an underestimation of the actual value because the second derivative is positive. That's all you need to say. There you go. The approximation would be an underestimate because the second derivative is positive. And the second derivative is positive because we have concave up. Maybe we should write that in there because that's not such a bad idea. Because the second derivative is positive, which means we have concave up. That's not what I want, which means P of t is CCU. Okay, that should be good. Okay, next, find the general solution to the differential equation, root b. All right, let's do it. We are going to do, we have to separate and integrate. So to separate and integrate, get all your b's on one side, all your t's on the other. So we'll have 1 over root b db is equal to dt. So I divided by root b and I multiplied by dt. Then I'm going to just rewrite this because I don't really like that looking thing. I'll do b to the negative half db is equal to dt. And now that my variables are separate, I can integrate them, and I end up getting out add 1 to this part, so add 1, and you get b to the 1/2 divided by 1/2. And when you divide by a fraction, you multiply by the reciprocal. So we're going to get b to the 1/2 with a 2 in front is equal to the integral of dt is t plus c. Okay. Let's solve for b because that's what we want to solve for. The general solution b of t means I actually need to get b of t equals whatever. So divide by 2. So you have the square root of b, or b to the 1/2, is equal to t over 2 plus c. Notice you don't have to divide c divided by 2 because c represents some number. And when you divide some number divided by 2, you just get some number. And now what you need to do to free up b is you need to do squaring. So b of t is equal to t over 2 plus the constant of integration squared. And that is your answer. So t over 2 plus c squared. Okay guys, this was a short one. Thank you for watching.